Hi everybody. Today's Pythagorean theorem day. That's pretty cool. I get to show you a very nice proof of the Pythagorean theorem. If we started with the right triangle looked like this one with a leg of length A and a leg of length B and hypotenuse C, you understand we're going to end up with A squared plus B squared equals C squared. It's a beautiful thing. Let me show you how that could happen. First, we're going to need to develop use those geometric means that we know about. So let me draw that altitude to the hypotenuse. And we just know that those triangles are already similar. I'm not going to argue about that. But allow me to call this length right there x. I got to break it into some parts. So if the whole thing is c and this part is x, so what would you say about this part over here? That's got to be c without the x, doesn't it? So it's c minus x. Let's write a couple proportions. I think it'll go very smoothly. Is A a geometric mean? You say, why, yes it is. A is a geometric mean between its part of the hypotenuse x and the full hypotenuse c. How about B? Is it a geometric mean as well? We're going to do some cross products right away, but let me write this other one too. B is also a geometric mean. I'll put it in the means positions then. B is a geometric mean between its part of the hypotenuse c minus x and the full hypotenuse c. Let's cross multiply, see what comes. A times A gives me A squared is equal to C times X. And if I cross multiply here, I got B times B is going to be B squared. And let's multiply these kind of carefully. C times C minus X, that's going to give me C squared minus CX. Now think with me. If these things are equal, and those things are equal, what if I add equal things to other equal things? Shouldn't they remain equal? Let's do that. I'm going to add this equation and this equation together. The left hand with the left and the right hand with the right. And look what happens when we do. I got A squared plus B squared equals CX plus C squared minus CX. Maybe you saw that coming. And lo and behold, the CX's fall off, and we got A squared plus B squared equals C squared. I know a couple other ways to prove that. But this is a nice one that uses the geometric means, and so it felt like the right thing to do. Actually, a little aside, I've been to the Rosenberg Library. I checked out a book that said 101 proofs of the Pythagorean theorem. Different presidents did so. It's just a clever thing for people to do, write different proofs of the Pythagorean theorem. I know a few, and I'll show you a couple of them. Here's one of them you saw today. Using geometric means you can get the Pythagorean theorem to show. But now we're going to work through a series of questions looking like this one. And it'll be kind of hard to sit through, but it shows you all the ins and outs of this. I'm going to use the Pythagorean theorem to find the missing length in each figure. C is the hypotenuse here, so this is going to go as you would have figured. 12 squared plus 16 squared equals C squared. I'm just going to show that process. That'd be 144. And 16 times 16 is 256 is equal to C squared. If you added those up, you get 400 is equal to C squared. And you take the square root of both sides, turns out that C would have been the square root of 400, which is 20. Straightforward. This is a little bit more interesting. Here they're given the hypotenuse, aren't they? That 34. And so I'm going to have to say that this one squared plus that one squared adds up to this fellow squared. So I'll go with 16 squared plus B squared equals 34 squared. I happen to know that 16 times 16 is 256. I have to call on a friend to get 34 squared. Alexa, what's 34 times 34?
34 times 34 is 1,156.
1,156. Okay, let's solve this little equation. I'm going to subtract 256 from both sides. That's going to work out kind of nice. If I subtract 256 from the left, I just got B squared. If I take 256 away from that, I've got 900, huh? Let's take the square root of both sides. And the square root of B squared is just going to be B. What about the square root of 900? Yeah, that's 30, isn't it? So that length would have had to have been 30. playing around a little bit more, looking at some of these lengths. Here again, I've given the hypotenuse. And that's when you got to be a little bit more careful. The sum of the squares of the lengths of the legs is equal to the square of the hypotenuse, meaning that a squared plus 12 squared would equal to 15 squared. A squared plus 144 is equal to 225. Subtract 144 from both sides, and you've got a squared is equal to 81. Take a square root of both sides, and I bet we're both convinced that a is equal to 9. Just burning through this little easy stuff. Now, going to get a little bit more interesting. Take a look here. We've got an isosceles triangle, and I've got an altitude drawn. And in an isosceles triangle, you would have to know that the altitude divides the base into two equal parts. I'm convinced that these two triangles are congruent, and this length would have been 8, and this length would have been 8. And I'm going to use the Pythagorean theorem on either one of those triangles. I'm going to use it on the left-hand triangle. You'd have to agree with me that x squared plus 8 squared would equal to 12 squared. Sometimes you get funny numbers when you use the Pythagorean theorem. Take a look at these. X squared plus 64 is equal to 144. Subtract 64 from both sides, and we got x squared is equal to 80. Take a square root of both sides and reduce that radical. Square root of x squared is just going to be x. What can you do with that square root of 80? It is 4 times 20, but better than that is 16 times 5. I know the square root of 16, so that'd just be 4 times the square root of 5. That's what this length x would have been. Got some kind of typical questions coming your way. Get a good look at them with me. Consider the broken telephone pole. Okay, so here's a broken telephone pole. And find the height of the pole. Use the measures that are given to find the height of the pole before it was broken. It's clear to me I'm going to have to figure out this length right there. And that's the hypotenuse of a right triangle. That's who we would call C if we're going a squared plus b squared equals c squared. So it'll set up as you expect. 14 squared plus 48 squared ought to add up to, I'll call it C for right now, c squared. I know 14 squared is 196. Alexa, what's 48 squared?
48 squared is 2,304.
2,304 is equal to c squared. Let's add these up. Oh, they add up pretty nice, don't they? 2304 plus 196 is 2,500 is equal to c squared. Taking the square root of both sides. A couple things you can think about that. I hope you know it right away, but if it's 25 times 100 is 2,500. I know the square root of 25 is 5. I know the square root of 100 is 10, so this must be 5 times 10 must be 50. Yeah, c squared is, the square root of 2,500 is just 50. That's what c would have been. But that's really not the height of the pole. I got to think, well, if I stood that pole back up, this would have been 50 more feet right there if that hypotenuse is 50. So it would have been 14 and 50. The original height, H-I-G-H-T, would have been 64 feet. You'll see a lot of trapezoids. They're a pretty fun way to play with the Pythagorean theorem. Here we have an isosceles trapezoid. And introduce the altitudes at either end of the upper base. You're going to do that a lot. Here's the upper base, and from either end of it, we're going to show an altitude to the opposite side. These sides are congruent. These base angles would have been congruent. There's lots of reasons to understand that these two triangles will be congruent. So I'm sure that this little piece right there is going to match with this little piece right there. And since this whole length was 10 and this whole length is 20, I've really built a rectangle in the center. This would have also been 10. So I think these would have been 5 and 5. I know if they got to add up to 20 across the base and this part was 10, these must have been adding up the other 10. And they're equal because these are congruent triangles in this isosceles trapezoid. They want to find the length of the altitude. I'm going to call the altitude A. And get serious with that Pythagorean theorem. I see it coming. A squared plus 5 squared would equal to 13 squared. Very friendly numbers. A squared plus 25 is equal to 13 times 13 is 169. Let's subtract 25 from both sides. A squared would therefore equal 144. Taking the square root of both sides, A must have been 12. That's what you call a Pythagorean triple. A 5, 12, 13 triangle. And geometry teachers depend on that stuff. I'll use those a lot. A 5, 12, 13. Other ones have shown up here too, some other Pythagorean triples. This is a 9, 12, 15, which is like a 3, 4, 5 triangle. You'll see more of those. We'll get that done. But you should be on the lookout for some triples that work. Whole numbers that solve the Pythagorean theorem. Consider the square at right. If each side has a length of 14, let's make this side be 14 and this one be 14. Calculate the length of the diagonal. Now, this is a square, so that's got to be a right angle right there, doesn't it? And since I got a right angle there, and I got this isosceles right triangle, I'm going to find the length of that hypotenuse. I'll call it D for diagonal. It is the diagonal. And it would be 14 squared plus 14 squared equals that diagonal squared. And 14 times 14 is 196, both times. So 196 plus 196 is equal to D squared. Add those up, and I guess that would be 392. Pretty sure that's true. That's 392 is equal to D squared. Take a square root of both sides. Now let's think about this for a second. Square root of D squared is just going to be D. Do you know any perfect squares that go into 392? Yeah, 196 does twice, huh? I should think of that as 196 times 2. And I know the square root of 196. In fact, 14 squared is 196, so the square root of 196 is 14. I do not know the square root of 2, about 1.414, but we don't want to use that approximation, so let's just leave it in the radical. So the beautiful answer here would have been the diagonal is 14 times the square root of 2. That's what this length would have been. You'll see a lot of similar stuff to that. Let me work some more. Here comes another one. In this square, the perimeter is 40. Find the length of each side and the length of the diagonal. If the perimeter is 40 and it's a square, I figure all the sides are the same. They must have been about 10 each, huh? So I'll call this length 10 and this length 10. There's a right angle right there. Now I care about the length of that diagonal. I'll call it D again. I'm thinking this one might be kind of similar to the last one, huh? I think those were both isosceles right triangles. So let's see if this works out in a similar way. I'm going to find the length of that diagonal. 10 squared plus 10 squared ought to equal the diagonal squared. There's 100. And another 100 equals the diagonal squared. So it's 200, isn't it? The diagonal squared is equal to 200. Let's take a square root of both sides. Square root of D squared just but D. You know any perfect squares that go into 200? Why, yes, I do. It's 100 times 2. And I know the square root of 100, so it's 10 times the square root of 2. Something for you to be on the look at. I'm going to go back to this last guy. When these were 14 and 14, that diagonal was 14 times the square root of 2. When these were 10 and 10, that diagonal was 10 times the square root of 2. They seem a little bit alike, don't they? How about this one, though? This is going to throw you a curveball. The diagonal of this square is 20. Find the length of each side. Give the perimeter an area. Let's see how we can do that. I don't know what these sides are. I'll say I'm going to call this A. I'll call this one A. Shouldn't they be the same? Because it is a square. And because these are the same, I'll call them the same amount, and I'll hit it with the Pythagorean theorem because I know I've got a right angle. So you'd have to agree that A squared plus A squared is equal to 400. Because that's what 20 squared is. So I know that 2A squared is equal to 400. Divide both sides by 2, and I got A squared is equal to 200. Take a square root of both sides, and A, that's how big the sides are, Hey, that's 100 times 2, isn't it? That's the square root of 200. I know the square root of 100 is just 10, so that'll be 10 times the square root of 2. That's what this length would have been, 10 root 2. This would have also been 10 root 2. Give the perimeter of the square. I think we can handle that. All the sides are the same. The perimeter of the square is 10 squares of 2 added up 4 times, or it could be 4 times 10 squares of 2. And that would just be 40 square roots of 2. There's the perimeter. Now what about the area? Well, if you want the area, you got to get the length times the width. Now, that'll just be, for the area, 10 square roots of 2 times 10 square roots of 2. And how do you multiply numbers with radicals? Outside guy with the outside guy and the inside guy with the inside guy. That would give me 100 square roots of 4. But I know the square root of 4 is just 2, so the area of this square is 100 times 2. It'd be 200. I'll say unit squared just to be good about area. And there's a little workout with that square, kind of interesting. You'll see a lot of equilateral triangles. These are really nice. Let each side have a length of 8 centimeters. Just going to label that to be 8, and this one's 8, and that bottom's also 8. Find the length of the altitude from vertex C. Let me show that altitude from vertex C. Altitude is by definition going to be perpendicular. And the altitude in an isosceles triangle bisects the base. In fact, we have a couple of congruent triangles there. Since this third side was of length 8, this part must be 4, and this part must be 4. You can trust me that the altitude of an isosceles triangle will bisect the base. True in this equilateral triangle as well. Let's call the altitude A. We're going to find the length of that altitude and the area of the triangle. It'll be fun. I'd hit it with the Pythagorean theorem in either one of these little triangles right there. This one or that one, they're going to work the same way. 4 squared plus, who's the hypotenuse here? The 8, then it stands alone. 4 squared plus a squared is equal to 8 squared. 16 plus a squared is equal to 64. Subtract 16 from both sides. We'd have a squared is equal to 48. Take a square root of both sides. Square root of a squared just a. What about that square root of 48? Well, let's break it down and find some perfect squares in there. It is 16 times 3. I know the square root of 16. It's just 4. I don't know the square root of 3 except an approximation. Let's leave it in the radical. So I'd say the altitude right there is 4 times the square root of 3. Pretty good to know about that. Give the area of the triangle. And you'd have to know ahead of time, and you probably do, that the area of a triangle is given by 1/2 times its base times its height. That'd give me the area of this triangle. So I'll put in some numbers, see what I come up for the area of this triangle then. The area of this triangle is going to be 1/2 times, and what's the length of its base? And the full base across there would be 8. And the height was 4 times the square root of 3. And if we just move from left to right, 1/2 of 8 gives me 4. So I have 4 times 4 square roots of 3. And 4 times 4 square roots of 3 is 16 square roots of 3. Unit squared. Because we always measure the area of anything in square units. Let's play again. Another equilateral triangle. The perimeter of this, they ought to be kind of similar, huh? They ought to work the same kind of way, but let's get through this one. The perimeter of this equilateral triangle is 36, and if it's equilateral, we know it's got to be, all the sides should be congruent, and they're adding up to 36, so they ought to be 12 each. Huh? Find the length of the altitude and get the area of the triangle. Let me drop that altitude. That's called dropping an altitude, by the way. And yes, the altitude in an equilateral or an isosceles triangle will bisect the base, so this length is 6, as that length would have been 6. I'm going to continue to call the altitude A and hit it with my friend the Pythagorean theorem. A squared plus 6 squared would equal the hypotenuse. We're working on that little right triangle equals 12 squared. A squared plus 36 equals 144. solve this for A. Okay, well, I'd have to get rid of that 36. I'll subtract 36 from both sides, and that would be 144 minus 36 is 108. Take a square root of both sides. And what can we do with that 108? You know any perfect squares that go in there? It's 36 times 3, as a matter of fact. You try some other stuff, but this is a nice one. If 36 times 3 is really 108, now I know the square root of 36 is just 6, but I do not know the square root of 3 any better than an approximation, so I'm going to say that A is 6 times the square root of 3. 6 square roots of 3 right there. Now, can you get the area of this triangle? I figure I could. Area of the triangle is going to be 1/2 times, hey, what's its base? And this base was 12. Well, what's that height? Well, that's 6 square roots of 3. Yeah, these two equilateral triangles are pretty similar how this is working, isn't it? 1/2 of 12 is going to give me 6 times 6 square roots of 3, and there's 36 square roots of 3. I got the area of that triangle, got everything figured out. This is kind of a clever question. Yeah, a lot of people think this is pretty important. I think it's worth talking about. Joe's got 3 squares, A, B, and C. Tell you a little bit about each one. Each side of square A is 8. So this is an 8 by 8 square right there. And the area of square B is 225 square centimeters. Well, that's this guy. The whole area is 225. So how big would the sides have to be? And if you knew that this side times this side gets you 225, it turns out that this side and that side would both have to have been 15. If it was a 15 by 15 square, then the area would have been 225. And by the same token, we could figure out with these links over here, we might want to ask Alexa, hey, Alexa, what's the square root of 324?
The square root of 324 is 18.
Oh, 18. So, that's 18 on a side. And find the length of each sides of squares B and C. And that I had to figure out that these two lengths both probably give me 324, so they must have been 18 a pop. So I know those lengths. If Joe joined the 3 squares together, would they make a right triangle? And what you have to catch here is the Pythagorean theorem is a biconditional. The biconditional is, well, the Pythagorean theorem says if it's a right triangle, then a squared plus b squared equals c squared. I'll say it like that. But the converse is also true. If the sum of the squares of the lengths of the legs is equal to the square of the hypotenuse, then it's a right triangle. And we're going to check out this one over here. If I laid these boxes together, you just make a crude little sketch, do the best I could. I'll make this one right here be 8 by 8. That's my 8 by 8 square. And adjacent to that one, I'm going to make my 15 by 15 square. This is 8 by 8. This is 15 by 15. And across here, I'm going to put the largest one. Just doing the best I can. You stay with me. And let that be my 18 by 18 squares. So, if I lay them together like this, the question that is asking me, would they make a right triangle? Would this be a right angle here? Does the Pythagorean theorem apply? And here's what we can do to make sure that that's true. I'm usually using what is called the converse of the Pythagorean theorem. If the sum of the squares of these two sides equals the square of that length, then by golly, that's a right triangle, and that would have to have been a right angle. Is it true that 8 squared plus 15 squared equals 18 squared? Turns out it's not true. 64 plus 225, is that equal to 18 squared? And 18 times 18? Hey Alexa, what's 18 times 18? 324. And these add up to 289. So these do not add up correctly. This is not going to be a right angle right there. Not being correctly. Truth is, this length would have had to have been 17. If I made a little sketch like that, let me show you that real quick. Maybe I could. Same idea. I got an 8 by 8 squared. That's why I was thinking that thing should have been 17 earlier. And over here is going to be another square. That's 15 by 15. If this thing were 8, and this one were 15 on a side, and this length were 17 on a side, would that make a right triangle right there? If this were a 17 by 17 square? And yes, sirree, I think this one would have worked it. Show me why you think so. Well, how about this? Is 8 squared plus 15 squared equal to 17 squared? Because if they add up correctly, and they did not last time, I got 289 on one side and 324 on the other. That was not a right triangle, not a right angle there. But how about this one? 64. 8 times 8 and 225. Hey, Alexa, what's 17 times 17? Alexa's out of a word, but it's just 289, I know for a fact. And these two add up to 289. So yeah, the sum of the squares of these two sides is equal to the square of that length. That is in fact a hypotenuse. That is in fact a right triangle. So if I put those together, and it was 8, 15, and 17, that's a Pythagorean triple. That would have made a right triangle. But here we would have to say, would they make a right triangle? The answer is no.